In this demonstration on the TI-Nspire CXII calculator, we are going to show how to program computing the power of a z-test. And to do this, we'll go ahead and do New. We'll add Program Editor. We'll select New, and we'll give it the name ZPower. We'll select a program, and we'll show it in the catalog. Now, when we go to program computing the power, there's a few things we're going to need to get from the user. So we're going to request that we get a null claim, and I will call that C. We're going to request the alternate claim. I'll call that M. We're going to request the population standard deviation. I'll call that S. We're going to request the sample size. I'll call that N. We're also going to request the significance level for the test itself. We'll call that A. And the last thing we're going to request is a test type, and I'll call that T. Now, for test type, I'm going to use -1 for a left-sided test, 0 for a two-sided test, and +1 for a right-sided test. So now we're ready to go ahead and perform our calculations. And the first thing that we need to calculate is kind of where this cutoff value is going to be in order to distinguish between rejection regions and non-rejection regions. So we'll go ahead and say if t equals -1, if it's a left-sided test, then I'll go ahead and select the library, and I'll do the absolute value, and I'll go ahead and type in the inverse norm because I'm going to need that z value for A01, and I'm using the absolute value for this because I'm going to let some subtractions take care of some other things later on. So we'll go ahead and do the inverse norm with the significance level getting the score, the z-score on a standard normal given that significance level. And I'm just using absolute value here just in case someone puts in a very large significance level. So after I do this, then I'm going to go ahead and compute that cutoff value. And that can be done by C minus Z times S. And I'll go ahead and use the fraction template over the square root of n. And then I'll go ahead and store this as x. I'll go ahead and say else if t equals 1, then we'll do something similar. We're pretty much going to have almost the exact same command. So we'll go back to the library, use the absolute value template, type in inverse norm to get the z-score for this. We'll go ahead and store this as z. And then we'll go ahead and do C plus Z times S. We'll use the fraction template to put the square root of n in the denominator, and then we will store this as an x value. And this is our cutoff in case we have a right tail test. And then another thing is the two-tail test. Else if t equals 0, then we'll go ahead and compute the cutoff again using the absolute value for inverse norm, but this time it's going to be A over 2. Remember, two-tail tests cut that significance level in half so that you're further away, and that is A over 2 on the standard normal 0, 1. And again, we'll store this as the z value. And when you have a two-tailed test, you now need to consider two different values for cutoffs, one on the right and one on the left. So we'll do C plus Z times S, and again we'll pull up the fraction, square root n, and we'll store that as X, and then we'll do C minus Z times S, again fraction template over the square root of that, and we'll store this as Y. Now this might seem redundant, but remember that even though you have the symmetry, if it's not centered at 0, then you can't guarantee that you're going to have a plus and a minus of that value. You could have a value that's centered at like 505, and then have one of your cutoffs at 510. Well, the other one's not going to be at negative 510, it's going to be at like 500. So you have to do plus or minus here, and you have to have two different values to store that in. Now, we're done with this particular if statement. So what we've computed so far is where my cutoff values are going to be for the on the original distribution claim. Now we have to use the new distribution, the one that's centered at the alternate claim, in order to compute the probability of a type 2 error and its complement, 1 minus that value, which is the power. So what we're doing here is we are going on ahead and getting our cutoff values first from the original claim curve, and then we are going to transition that information over to the new curve, the curve that's centered at the alternate claim, and then we'll compute our areas under that curve. So now we're going to go through some more if statements. If t equals -1, then we'll go ahead and say that the norm CDF from the x value to all the way to infinity, and you can kind of simulate infinity with doing the e number, the mantissa exponent, 1e99. This time it's centered at the alternate claim, which we've labeled at m. Okay, remember our alternate claim is at m here. And then we go ahead and use that standard deviation, s, and again we'll use the fraction template over square root n, and we're going to store that as b for beta, if you will. And then we're going to go ahead and display beta, probability of a type 2 error, and we'll use lowercase beta here. We'll go ahead and display that beta. You know, normally when you display beta, you're also interested in displaying the power, which in this case is just 1 minus beta. Now we'll go ahead and do else if, and this is what happens when t equals 1, which is similar to this case. We'll go ahead and do, again, the norm CDF. But this time, when we're doing a right-tailed test, we want the area left under the curve. When we do a left-tailed test, we want the area right under the new curve, because that is where we are trying to determine the probability of a type 2 error. And a type 2 error, remember, is that you fail to reject the null claim when in fact that null claim is not accurate. So we're kind of switching our thinking around a little bit here. So here we're going to go -1, go back to that mantissa exponent, go 99. Oop, cursor is in the wrong spot. 99, all the way up to the x value, and again we're centered at the alternate claim on this curve, and we're going to compute the standard deviation using the sampling distribution. And again, we'll store this as b again, and we'll go through the same commands as before. Display beta as b, the probability of a type 2 error, display the power as 1 minus that b. And then we have else, and I'll go ahead and do else if here as well, t equals 0, then now we have to go through and do a little bit different, because now we have two tails that we have to concern ourselves with. Now, the probability of a type 2 error when you have two tails is going to be between two values. So we're going to say norm CDF from -1, go back to that mantissa exponent, 99, all the way up to the x value that we compute when we have a two-tail test. This will be centered at the alternate claim, and the standard deviation is from the sampling distribution. So we'll go back to that fractional and do s over square root n. Close that out, and then we'll say minus a very similar thing, norm CDF, -1 mantissa exponent, 99. This time we go up to y. Now, we formulated x so that it's automatically bigger than y, because x has c plus a positive value and y has c minus a positive value. So y has to be less than x, and that implies that the area under the curves will also be positive once you subtract these two values. So again, we're typing in our information where we have square root n. Get out of that. And then again, we're going to store this as our type 2 error probability beta. And then again, we just display beta, comma b, and then display power, comma 1 minus b. And then we need to end the if statements. So at this point, we now have just kind of a basic overall program for computing type 2 error and computing power of a z-test. So now we just have to test it. So what we're going to do is we're going to go to menu, check syntax and store, and it says it was stored successfully. And all that means is that it is now accessible. And if there are any other errors, then we may have to go in and fix them. So let's test to see if there are any other errors. So we're going to go to menu, and we'll go to run, if you will. So we'll go ahead and ZPower, and now it's asking for a null claim. And I'll just take an example from one of my textbooks here. Let's say that our null claim is 515, and our alternate claim is 530. Our population standard deviation will be 114. Our sample size will be 40. Our significance level will be 0.05. And let's say that I want to run a right-sided test. So I'll do test type equal to +1, and it gives me these values. So it outputs all the information we typed in, and then it outputs the beta at 0.7917 approximately, and then it gives me the power, which is a complement of that, at 0.2082 approximately. And because I'm pulling this from a Michael Sullivan statistics textbook, this particular example, I can confirm that this answer is accurate. So right now that works, but this is just one of the options. We typically want to test other options that are available as well. So we'll go ahead and do ZPower, and we're going to test a left-sided situation this time instead of a right-sided situation. So using one of the problems from Michael Sullivan's textbook to test this, we'll go ahead and do a null claim at 50, An alternate claim will be done to be 48. Our population standard deviation will be 12. Our sample size will be 24. Our level of significance, we'll keep that at 0.05. But this time we're going to run a left-sided test, a -1. And again, we get our information that we typed in. We get our beta, probability of a type 2 error, and our power at 0.2037 approximately. And again, this is accurate to the results I'm seeing in the textbook that I'm using as my example. Again, there's a third option, the two-tailed test, so we'll go ahead and test that one as well to make sure that it's also working accurately. And this time, we'll have a null claim at 100, and our alternate claim will be at 103. Our population standard deviation will be 7. Our sample size will be 23 this time, but this time our level of significance will be 0.01. And our test type will be 0. I selected 0 to represent a two-tailed test. And what we have here is, again, we have the information. We have our probability of a type 2 error at approximately 0.698. And we have our power at approximately 0.30. And these are, again, accurate with the examples that I've pulled from Michael Sullivan's textbook on statistics. And this is one way that you can program in computing the probability of a type 2 error and computing the power of a z-test on the TI-Nspire calculator.